Hello and welcome to another Senior Curriculum Inspiration, proudly sponsored by Texas Instruments Australia. The Curriculum Inspiration series is designed to help teachers to develop strategies in the effective use of Texas Instruments calculators in the classroom with carefully selected mathematical activities. My name is Chris Irison and I will be your presenter for this session. Today we will be focusing on the activity titled Learning Exponentially, and I'll be using the Texas Instruments CX CAS platform throughout the activity. The components of the activity consist of a student worksheet, a teacher worksheet with helpful notes in blue about the activity, and also the answers in red for the activity. As well, a TNS file for students to explore throughout the activity is included. It's now time to start exploring the activity. What happens to the graph of an exponential function when it is dilated, reflected, or translated? What combinations of these transformations are homomorphic? Students will use the dynamic TI-Nspire technology to visually and numerically explore these transformations. Part A. Students will explore the relationship of y equals b to the power of x. Students are asked to navigate to page 1.1 of the TNS file and are given a series of questions to answer. This is question 1. There are 5 parts that students will investigate for this page 1.1. Let's go and have a look at the TNS file. Question 1 says, as the base b is changed from 2 to 10, part A is describe what happens to the points 1, 2 and -1 are half, which is shown on the screen, by consideration of the ordinate or the y coordinate. So you notice on the page that we have some sliders shown, and if we have a look at the moment, b is set to 4, and if I click on this, b will increase to 5, 6, 7, 8, 9, 10. This is where the TI-Nspire software and calculator are really good as visual techniques for understanding what's going on. For the 1.12, we noticed that as b increases, the ordinate increases, and for the point -1.5, the reverse occurred. The next question asks which points, if any, are invariant. The only point on the graph that does not change at all is the y-intercept, or the point 0.01. The next question is describe what happens to the points 1, 2 and -1.5 by consideration of the abscissa, or the x-coordinate. Here we're going to use the swap slider to show that we can see what happens to the x value. I'm just going to set this back so we can see what happens. And then as we increase b, we can see instantaneously what happens to the red graph. So we would say the answer to the question would be for the point 1, 2, as b increases, the abscissa decreases, and the reverse is true for the point -1.5. Note that all points are moving towards the y-axis. Let's just see that again. And students will be playing this over and over to see what's happening. So as b increases, we see that the graph is moving towards the y-axis from the positive and the negative side. Part D of this question says, describe what happens to the shape of the graph as b is changed. Hopefully, students will come up with the idea of what we've just seen. As b increases, the graph is dilated towards the y-axis, parallel to the x-axis. We're using the slider, which is showing it moving horizontally there, to answer that question. The next part is identify any asymptotes for each of the graphs. The only asymptote that we know is there is that y equals 0 along here. If students can't see that, they might like to set up a table of values. And if we just press Ctrl+T, this will appear. And as they scroll through, I'm just going to split the pages up so that it looks a little bit bigger. And as we see, as the value of x decreases, the value of y is approaching 0. And that's a nice way that we could show what's going on. Part B is exploring y equals 2 to the power x plus c. And the students will go through a range of values for c to see what's happening. The first question says, describe what happens to the shape and location of the graph. So as the student sees that c is set to 2, the two graphs are clearly labelled here. The f2x equals 2x plus c, and f1x is the unchanged graph. As we change, we see that the graph is moving upwards as c increases. The same would occur, it would move down as c increases. We notice that the shape of the graph is not changed as there are no dilations. The location of the graph has changed. The graph is being translated parallel to the y-axis by a quantity of c from the x-axis. Sometimes students may not be able to see this, so there is another slider which says show. In this slider we see that the distance between the points on both graphs is shown, and as we increase the value of c, we see that that distance remains the same. We are to identify any asymptotes for each of the graphs. One thing to note is the blue dashed line here, which is the asymptote, does not normally appear as you type in the equation. It has been inserted manually and pre-entered into this TI-Nspire file. As you can see, and the students will see that the asymptote is y equals c. The next question was, for what range of values for c does f2x equals 0 have a solution? The students are only asked to do this visually with what they have there, and they will see that if c is less than 0, we will have a x-intercept. Okay, part C is about exploring the relationship y equals 2 to the power x minus h. This time, students will move the slider h, and as we increase it, we will see that the graph is moving. It's now on top of itself, equals 0, h equals minus 1, it's going to the left, etc. Students may not be able to see this easily, so again, we've put on 2 points on each of the graphs and showed how this distance will change. And hopefully, if students can pick that up themselves, to visually see what's going on. The question was, describe what happens to the shape and location of the graph. The shape of the graph is not changed at all, as shown there. There are no dilations, but the location of the graph has changed. The graph has been translated parallel to the x-axis by the quantity h from the y-axis. We are to identify any asymptotes for each of the graphs. The only asymptote there is, again, y equals 0, as there are no vertical translations. We move on to the next part. We're now going to examine y equals 2 to the power of mx. If you look on the screen there, there's a few more sliders to look at as well, and we're going to compare the functions of f1x equals b to the power x, f2x equals 2 to the x, and f3x equals 2 to the mx. The purpose of this exercise is to highlight the homomorphic representations for these transformations. Question 4 says, as the values of m is changed from 1 through to 4 in the graph of fx equals 2 to the x, describe what happens to the shape and location of the graph. We see that the location of the graph is unchanged, as there are no translations. The shape of the graph, however, is dilated towards the y-axis. There's also a dilation factor, which students may not pick up at the moment just by looking at this as changing the values, but a dilation factor of 1 on m parallel to the x-axis or towards the y-axis. Students will replay this several times before they might be able to see what's going on. Are there any invariant points? We see as the black graph is changing, it still passes through the same y-intercept at 0, 1. There is a hide show button, which you can use to remove the blue graph. It is there. The next part of the question wants you to explore values of m and b to determine values for which the graphs are homomorphic. So if I see where m equals 3, it lines up with the blue graph there. If I change it again, I might put m equals 4, and I keep changing the b value until it matches up when b equals 16. Okay, going on to the next activity part. In this point, students are going to explore the relationship between y equals a times 2 to the x. We are to explore the relationship or the values of a and h for graphs of f2x equals 2 to the x minus h and fx equals a to the 2x. Determine the values for which the graphs are homomorphic or the same. Explain the outcome and identify any limitations for the comparison. As we go through this slide and we change the values, we see that that's our standard graph, h equals 0. If we play with a equals 1, we see that it's moving in 0.1 values, and when they're on top of each other, we see that a equals 2 and h equals minus 1 all agree. We could go to h equals minus 2, and we see what happens as the graph changes. And when we're at 4, we see that they're homomorphic again. One thing to note, that as the value decreases, right down, and students get to that and move in the other direction, they'll find that when a becomes negative, we get a reflection in the graph. Okay, going on to part F, combining transformations. In this part, students are given 2 graphs on the screen, and they are to put together all the ideas that they've found out so far about transformations, dilations, translations, and reflections. And they are to put in on a blank page that has been included in the TNES file and try to work out what's going on. I would encourage these students to solve these questions graphically rather than algebraically, as they can visually see the effect of changing a parameter. Alternatively, a student might wish to solve it algebraically, but if they do this, they will get the answer, but they won't be able to see anything going on visually with the graph. They may, however, solve it algebraically and then go back to the graph to try and see what's going on as they plot the things. A student may decide to solve it using sliders graphically, or just try and attempt to put in values starting with y equals a to the power 4x and then changing it to 4 to the power negative x, and then see that that's a reflection in the y-axis. They'll then continue to work out the values of a and c. Clearly, the student will see that for the g of x graph that c equals 0. Question 9 is another graph that is there, and it's a little bit more complicated, so students will have fun exploring that one. I hope that you've gained some useful ideas that can be used in your classroom to inspire your students from this curriculum inspiration session. That's all we have time for today, so please visit the Texas Instruments Australia website for more free activity lessons that make students explore, discover and visualize mathematics using the Texas Instruments technologies. And for when the next curriculum inspiration is scheduled, goodbye for now.